Hey team, so our next concept we're going to be going into, or set of concepts, is about energy changes. So we've looked at particles and how they give certain substances their properties. The last bit of this achievement standard is about energy and the fact that when a chemical reaction occurs, it either releases energy or absorbs energy. So with the experiments we've done in science in the past, hopefully we have realised that some reactions feel hot. They give off some heat energy. And others feel cold. If you were to put them in your hand, they'd feel cold. Now, while these aren't chemical reactions, I'll give you some examples. If you were to put some ethanol or alcohol or ice on your hand, then it does a physical change and they feel cold. They're absorbing the heat energy out of your hand and they're changing state, evaporating, or in the case of ice, melting. Conversely, and we're not going to do this, if we put our hand into some fire, it feels really hot. And the reason for that is it's releasing so much heat energy that goes into our hand, and that's what burns us. The fact that our hand absorbs that heat energy that has been released by the chemical reaction. So we have names for these two things. The ones that feel hot and give off energy are called exothermic. Exo, as a prefix, means outside, and thermic, as a word, means to do with heat. So, this pushes energy or heat outside the reaction, so it will feel hot. The opposite to that is endothermic. Endo, as a prefix in science, means inside. So, they take heat energy and pull them into the chemical reaction. The way we measure these energy changes is using a thing called enthalpy. So rather than energy changes, we probably should be calling them enthalpy changes. And enthalpy, because it's to do with the total amount of heat involved, hence these words thermic, has got the symbol H. And enthalpy is basically all of the energy we find in the chemical bonds, and that's called chemical potential energy. So that chemical energy is in the chemical bonds, and it's to do with the kinetic energy of the particles, and that's what links to the past part of our topic, the kinetic energy of the particles. Put those two things together. Now there is a bit more to it, there's pressure and a few other things there, but we don't do those at high school level. Put those two things together and we have a measure of our enthalpy. We realise it, or we understand it, by measuring how much something gets hotter or colder, working out how much we have of that substance, and then we can work out its enthalpy change or its energy change. And the unit for that, I've run out of space, I'm sorry, so I'll just put it below it, is the kilojoules, and that's the amount of energy per mole. And a mole is just an amount of a substance, and we're going to cover that in more detail in a future part of this topic. The mole, M-O-L-E, it's not much of an abbreviation really, is it, to M-O-L, but the mole is something that might be something worth looking up, just so you have a bit of prior knowledge to that. So, the best way to represent exothermic and endothermic reactions are as graphs, and we need to be able to sketch these. So in an exothermic reaction, the particles that we start with have got a lot of energy already, normally within their chemical bonds. So they start with a really high energy level. Lots of enthalpy in the reactants. And I'll put the S in brackets there simply because sometimes you only have one reactant. For example, the auto-oxidation of hydrogen peroxide, which breaks down into water and as steam and oxygen. Then after it reacts, the energy of the products is much lower. So we end up having a reduction in enthalpy. So here is our enthalpy change. We use a triangle, which is actually an uppercase delta Greek letter. Enthalpy change is shown by this thing, delta H, and you'll see that it is negative. It's going downwards in the graph. Conversely, an endothermic reaction, again we have enthalpy on our y-axis in kilojoules per mole. The reactants for this are much lower, or energy I should say, of the reactants is much lower. Then you pump energy in, they absorb energy and they react, and they end up with products with a much higher energy level or enthalpy. So we can see there that the enthalpy, if this is our enthalpy axis here, has clearly gone up. So our change in enthalpy is positive. And that's most of the story until we realise that, actually, hang on, in year 11, didn't we learn that you had to provide particles with enough energy for them to collide successfully in the right orientation so that they would react? So all of these reactions actually need an input of energy to start with. And that makes sense because we don't see things like wood spontaneously combusting, just catching fire for no reason. You have to give it some energy to get it started, to activate the chemical reaction. And that's exactly what this thing is called, activation energy. So we're going to add into our graph a thing called activation energy, or EA. And basically, this is the energy required to start the reaction. And we're going to learn about the impact that things like catalysts and so on have on activation energy and how they do it. But basically, it's about giving enough energy to start the chemical reaction. So, let's say the amount of energy required for this reaction is here. So I'm trying to use color coding here, my blue one. Before this reaction can even occur, I need to heat it up to that level, and then the reaction will occur. So end up with a graph that looks something like this. It's got a bit of activation energy here, so it needs a little bit more energy pumped in, and then it will react and give us lots more energy, normally as heat, out. To kickstart an endothermic reaction takes a bit more because everything starts at such low enthalpy to start with. So if my EA for this one is up here, I've got to get it all the way up here before it will react. So there's a little bit more, there's a lot of energy required. Here's my activation energy. So for this one, my activation energy is just adding a little bit more, and this one it's adding a lot more. And then it will just keep, even as the reaction's occurring, it will keep absorbing more and more heat energy for it to carry on. Now, these principles are covered on pages 100 to 103 in your SciPad. They also include some sketches of those showing you where the activation energy is and so on, showing us that we consider this to be our activation energy here, and this to be our activation energy here. Notice that they're both positive values. They also give you some good examples of some chemical reactions and physical changes which are representative of exothermic and endothermic reactions. You would need to be able to tell from either an enthalpy change value, so being positive or negative, you'd need to be able to tell whether it's an endothermic or exothermic reaction. And as we learn more about the mechanics of a chemical reaction, about the chemical bonds being made and broken, the state changes of state, so solid to liquid, for example, you'd need to be able to say, oh, that absorbs energy, that would be endothermic. So linking it to enthalpy change, being negative or positive, and linking it to absorbing energy or releasing energy. The easiest way I can the best hint I can give you is if it feels hot, then it's releasing energy. Your body is absorbing the energy that's left over, so it's exo. If it feels cold, then it's absorbing energy out of you, so it's endothermic.